Dear students and friends, I would like to welcome you to the Elias Kyriakides Memorial Lecture, which is an annual event organized by the GEOS Research and Innovation Center of Excellence, the Department of Electrical and Computer Engineering, and the University of Cyprus, to honor the memory of our beloved friend and colleague, Professor Elias Kyriakides. We envision that this annual event will provide an opportunity for many of the Elias students, collaborators, and friends to get together to remember him and think of ways to continue his legacy. Due to the COVID-19 pandemic, we have restrictions, and as the number of people that can be physically present in this room for this lecture. So the event is also broadcasted, and we have several people following it online. Hopefully next year we'll be able to accommodate everybody and have the event fully physical present. Since the very early stages of his career, Elias was striving for academic excellence. He graduated from summa cum laude in all of his degrees, bachelor, master, and PhD in electrical engineering, all with 4.0. He won a number of awards, the Cyprus Presidential Award for ranking first among all the Higher Technical Institute graduates in 1996, the Alumni Associate Award for ranking first among all Spring 2000 bachelor graduates at the Illinois Institute of Technology, the Palais Outstanding Doctoral Student Award for the best doctoral graduate of the year of 2003 at Arizona State University, USA. After his PhD graduation, he worked at ASU as a faculty research associate from January to July 2004. And in September 2004, he joined the newly established Department of Electrical and Computer Engineering at the University of Cyprus, where he reached the rank of an associate professor. During his tenure, he worked tirelessly towards the success of the department, leading teaching and research activities in the areas of power and renewable systems, as well as undertaking many administrative and outreach activities for the department. Elias was also a founding member of the GEOS Research and Innovation Center of Excellence. His research area was in electrical power systems and emphasis on wide area monitoring and control, power system operation, and the integration of renewable energy sources. The power group that he has established at GEOS continues strong and remains quite successful. His work is internationally recognized and widely cited. He has almost 6,000 citations according to Google Scholar. He has published more than 200 articles in top journals and conference proceedings in this area. He has also published 4 books and was granted 2 patents. Professor Elias Kyriakides was awarded more than 30 research projects, of which he was the coordinator in 19 of those. His total funding share was more than 5 million euros, without including the GEOS teaming project, which also accounted for 40 million over the 15 years. As a result of his accomplishments, he was elected fellow of the IET and senior member of IEEE. In May 2009, he was elected the action chair of the ESF Cost Action Analysis, Intelligent Monitoring, Security and Control of Critical Infrastructure Systems, with participation from 30 countries and more than 185 researchers. He served as an associate editor of the IEEE Systems Journal and editor of the IEEE Transaction on Sustainable Energy. He has led a team of engineering and MBA students that received the 2nd prize in the Cyprus Entrepreneurship Competition in 2010. Finally, he served as a chair of the IEEE section, as well as in several other positions. The list of his accomplishments and the numbers, although outstanding, do not come close to describing the wonderful personality of Elias. A distinctive, kind and giving individual, an exceptional human being, a spiritual person of integrity and uncompromised values, a talented teacher and great mentor to his students, a supportive and stimulating colleague, a beautiful mind and an exceptional researcher, a great friend. We greatly miss his wonderful smile, his kindness, his willingness to help, and his perpetual optimism. And with these words, I would like to express our gratitude and honor for all of your participation here and also the people from online. And I will take this opportunity right now to thank Elias students, Marcos and Lenos, as well as our colleagues Christiana and Skevi for their effort for organizing this event. Of course, special thanks go to our distinguished speaker, Professor Jovica Milanovic, who flew in from Manchester, UK, delivered his lecture in Elias' memory. It's great to be able to fly again and be able to have these physical meetings. Today's lecture by our distinguished guest is very much related to the research goals of Elias towards resilient net zero power systems. Professor Jovica Milanovic received his diploma engineering and MSc degrees from the University of Belgrade, Yugoslavia, the PhD degree from the University of Newcastle, Australia, and the DSc degree from the University of Manchester, UK. Prior to joining the University of Manchester in 1998, he worked with Energo Project Engineering and Consulting Company and the University of Belgrade in Yugoslavia, and the Universities of Newcastle, Tasmania in Australia. Currently, he's a professor of electrical power engineering and deputy head of the Department of Electrical and Electronic Engineering at the University of Manchester, and visiting professor at the University of Novi Sad and University of Belgrade, Serbia. He was chairman of 5 international conferences, editor of or member of editorial and technical boards of more than 70 international journals and conferences, research project assessor or panel member for numerous international government research funding councils, member of 9 past or current IEEE, SIGRAM, SIRE working groups, and consultant and member of advisory boards for several international companies. Professor Milanovic participated in or led numerous research projects with a total value of more than 80 million sterling pounds. Published close to 600 research papers and reports, gave about 30 keynote speeches at international conferences, and presented about 150 courses and tutorials and lectures to industry and academia around the world. Professor Milanovic is a chartered engineer in the UK, foreign member of the Serbian Academy of Engineering and Sciences, fellow of IET, fellow of IEEE, distinguished IEEE PES lecturer, member of and past chair of the IEEE Herman Halperin Transmission and Distribution Award Committee, associate editor of IEEE Transactions on Power Systems and Power Engineering Letters, and a member of IEEE PES Industry Technical Support Leadership Committee. He was a member of IEEE PES governing board as regional representative for Europe, Middle East, and Africa for 6 years, and a member and vice chair of the IEEE PES Fellow Evaluation Committee. Starting in 2002, Professor Milanovic will be an editor-in-chief of IEEE Transactions on Power Systems. And without any further ado, I would like to give the floor to Professor Milanovic for his speech.
Thank you very much. Thank you, Christos. Before I start talking about anything else, I'll ask your permission to take the jacket off. Otherwise, at the end of this talk, you will have boiled lecture. That's not pleasant, neither for you nor for me. So I do apologize. I have to take this off. It's too hot.
I didn't even bring you.
Yeah. So. I'm coming from a very, very cold country. Right. So it's really. It's fine. Thank you. It's really great honor and pleasure to be here, talk in a lecture dedicated to Elias Kyriakides, great friend of mine, and you will see in some part of my talk I will be addressing some of the issues that he was famous for, and based on the book that he published a few years ago, which was very inspirational for me. I'm very glad also to be in Cyprus again. This is not my first visit. This is not the first visit to Nicosia. And even more so, I'm very glad I can travel again. After almost 2 years, this is the second time that I'm traveling on business. and to a friendly country and to visit friends and talk to you about some of the work that my team and I are doing in the global area of resilient power systems. So I will very briefly go through, excuse me, the introduction. What is it that is making systems more challenging, I would say, today than ever before? And then I'll go through some examples of the work that we are doing in various areas identified along the way. So the first thing is drivers for changes in design. And this is something that whoever, and I'm sure everyone in the room, has written papers and read papers about trends in energy systems and power industry. So these are the things that everyone is talking about. So changes in market, renewables, different type of loads, connection of new types that we don't have enough experience with, integration of different vectors, energy vectors, gas, heat, not necessarily energy, transport, social, communications with power, which makes systems much more complex. And of course, data security. Data security, which became particularly important, and we all witnessed that over the last 18 months or so, when we rely on communication systems, Zooms, Teams, WebEx, name it, for everything that we do. So data security becomes particularly important, not only for our everyday communication, but for running our systems. Now, the other thing, which is coming into a fora more and more prominently, is system integration, or rather systems integration. And this is one of the things that I believe are very close to Elias Kyriakides' heart. So we have a power network, then we have a communication network, which is, they go together. They have been going together all the way through, because they can't work one without the other. In particular, power system has to be monitored and controlled. So there are connections between the two. Then we started talking about gas networks and other set of connections. We could go further to connect different levels, including social networks, which are not shown here. And now all this together is becoming something that people are more and more trying to understand. I think that the use of word understand is not accidental, because claiming that we know how to solve a problem of a network like that, I believe, is overambitious. I think the more important thing is to understand first what's going on there and how these connections work, and then to try to solve it bit by bit. Because at the end, this is the network that we will have if you put all connections in. And then the question is, as Robert De Niro said, how do you do this? How do we analyze a problem like that? In order to analyze any problem, you have to understand it. You all know, younger colleagues in particular, older as well, that the half of the answer is understanding the question. So the big thing with interconnected systems, with systems of systems, with interconnected critical infrastructure, is to understand what the question is. And I am trying, with people working with me and with some other colleagues, to understand the question. And then we can start searching for solutions. I'll show you later on how we did it. Now, in a system like that, which is becoming reality, which has been around us all the time, but we haven't looked probably in depth of how the system like that worked. We were siloed. Power engineers were looking at the power system, transport engineers were looking at transport, gas in gas networks, heat engineers in heat networks, communications engineers who were involved in all of that tend to work in communications, satellite communications, not really communications relevant to one of these engineering or energy systems. Now, people are encouraged by governments mainly to start looking into the whole system picture. And looking at that whole system brings again the question of resilience. So what is resilience? And if you pay attention, well, not pay attention, if you're listening what people are talking, these days they're talking about resilient energy supply, resilient system, etc., etc., etc. Resilient, you know the definition, I'm going to read for you. It's how to save the system if something happens in zillion years and cause huge impact. I'm obviously modifying the words a little bit. So it's about high impact, low probability event and making sure the system survives even events like that. Now, one thing is that isolated system survives that. And the other thing is when you look interconnected system or system of systems. And obviously there are different ways. How do you measure the impact? So the metrics used traditionally are one way or the other, evolving around probabilities. You know, how likely is something to happen? What is the duration of problem? How frequent is the problem? Is it once a year? Is it like in 50 years? And what is the probability of that event to happen again? Now, when you say once in 100 years, event in once in 100 years. So we may have one this year. And then if we have another next year, is this 2 in 100 years? Or the last ones was at the end of 100 years? And this year's one is at the start of next 100 years. So how do we, which 100 years are we talking about? So where is the time frame within which we specify low probability event? That's another question we have to agree on. But the thing is, it's about probability and it's about the length of the problem that we are experiencing. But then the other thing with low probability, high impact. So what is the impact? Impact is money, is social. It may be geographically constrained. One city, one part of the city, one part of the country, several countries. And then there are impacts on health and safety, which is probably the most difficult to assess. Now, if you want to do a comprehensive assessment of the impact, then all of these here, economic, social, geographic, health and safety, have to be taken together. One of the big pushes at the moment that UK electricity and gas regulator is insisting on with distribution and gas and electricity transmission companies, business plan, new business plan for new regulatory period. We've started for transmission system this year, and we'll start for gas. Electricity transmission gas started this April, and for distribution companies will start next April 2023. Now, what they are insisting on is social rate of return. So assessment of social benefits, global social benefits of any action taken. So either global social benefit or global social impact that talks about including various different aspects of the effect which happens now and then. Now, the other thing which we traditionally didn't talk about in the past was the other two. We talked about network resilience. Network resilience is not a new topic. It's been around for many years now. What we hear more and more in discussions with industry in particular, with regulators, with government, is the second thing, workforce resilience. Whether we have a workforce that is resilient from various aspects, and the levels of workforce resilience include, but not limited to, equality and diversity, job satisfaction, whether it's how do you feel at work, or whether you are well paid at work, how you're treated, and so on. And then obviously the more recent thing, cyber resilience. Now, all these three, when you think about that system of systems, about the interconnected system, all these three work together. So you can't talk about resilience of a system without considering technical aspect, which is network, social aspect, which is workforce, and then the final one is communications, cyber, because we are obviously totally, if you like, exposed to IT systems and IT communication. So the resilience of the system of systems will depend on various things that can happen, including pandemics. Now, pandemics is something that we knew about these things, you know, pandemics existed, but we thought, well, that will never happen to us. And then what happened? For the last 18 months, the world practically stopped. So a lot of things had to be changed, had to be adopted. We had to adopt to different ways of doing things. We are still doing things differently, obviously, and it will continue for some time. Now, putting all this together in a system which is not electrical system, which is not gas system, which is not communication system, and trying to solve it. Know how. So that's why I said the important thing is try to understand first what's going on there. What are the important bits? Not everything is equally important, but which ones are more important than the others? And then trying to solve the important bits first, then less important, then the least important. But you have to be confident that you know how to assess what is the important thing. Now, so in this environment, coming back from a global perspective of interconnected systems, let's deal with one by one. So the closest to me, or the one that I think I know the most about, is power system. So how is power system today different from what it was tomorrow, and what was yesterday, and how will it be different tomorrow? So these are the things that you all know about. Again, I'm not telling you anything new, probably emphasizing one of the things over there, data. We've been monitoring systems all the time. There are measurements, devices, or time internal. But now we have more. And somehow, over last 5, 10 years, we realized that it's not about having the measurements. It's kind of making something useful of them. And then people started putting more and more monitors. So data were coming. And say, when you go to industry, do you have these measurements about business? Yeah, sure we do. So what do you do with them? Well, if we have a problem, we go and analyze it. Now, again, because of various reasons, I'm not going to go into now, or not in detail, people started looking more closely on what all these data that we are collecting can be used for. And then the next question came, which is, okay, fine, we are collecting data now. Let's use this data. But then we have been collecting data forever. So why don't we use the history, the legacy data as well? Now, the issue with legacy data is many of them are saved by different departments in different formats. Some were text-written notes about the causes of fault, about the consequences. So to process that, it takes a lot of time. But then there are colleagues working in the area of computer science and data analytics who are researching text recognition. So reading text, extracting meanings and feelings, believe it or not, sentiments from written text. So when you talk to them, they say, well, if you can read prescription written by a doctor, by a physician, why can't you read the report written by an electrical engineer or gas engineer or mechanical engineer? So if you can use the data in a different format than in numbers only, and combine that with numbers, who knows what you can learn. Now, I'm going too far now, obviously, because we still haven't mastered how to use numbers alone, because of the huge number of numbers that we have. But putting all this together, all these numbers that are coming from various monitors all around the place, with some of the legacy data, which are in different formats, and trying to get information from them is becoming critical. Because investment in monitoring, however large it may be, will depend, in many cases, on individuals willing to accept the monitoring devices. I'm sure you all know what I'm talking about. Smart meters. The rollout of smart meters didn't happen at the rate as people thought it will. So many countries have installed many smart meters, but not all of them. There are still people who don't want them. And if you don't have good coverage by smart or other meters, however you want to call them, you don't have full observability of the network unless you are using what you have, process the data in a clever way, and extract the information about the parts of the network that are not covered by monitors. And this is another area where the pressure is coming from regulatory and governmental agencies to the network operators to increase observability of the network. Initial response by all network companies was, yes, of course, we will do that. We will install more monitors. And then the government, and others say like, yeah, fine, that is a solution. Put the more monitors in, apply fast processing techniques, and that will work. But what will happen if you can't actually install more monitors because people don't want to accept it? Because they're all talking about smart meters. And then the pressure comes now. There were discussions a few months ago, and then there was a feedback from regulatory agencies and so on, and people are revising their position, how to increase observability of their networks without necessarily installing more monitors. So can we use something else in addition to monitors to learn about the network observability? Now, so the first challenge is, in this aspect, how do we handle data which we have, which can be in different formats, and which keeps coming, either the number of numbers or text or whatever, they keep coming. And the other thing is data, when you're talking about power system, doesn't have to be only measurements of voltages, currents, powers, angles. The data about the system are also opinions of customers. Willingness of customers is a different thing. So I'm not talking here of understanding and analyzing only the data related to technical operation of the system. I'm talking about the data relevant for system as a whole, for the operation of the system as a whole. We are still far behind in understanding how to incorporate all this together. But if you want a step ahead, that would be a step, including customers' perception, users, stakeholders' views on how and what the system should do for them with what the system is actually doing, and try to make forward the decisions about solving these issues. So data analytics is the area which is not going to go away. It's only going to grow. And this is something, as I suppose many of you here are aware of, it's not something that electrical engineers were necessarily fully trained in. This is more something coming from the area of computer science, maybe mathematics, maybe some other areas. So we would need to get more closely. We will start to collaborate more closely with people from other areas. Now, the other thing is uncertainties. Uncertainties, again, this is something which existed in the systems before. Systems were always a little bit uncertain. But the thing now is the uncertainty because of different types of generation, as you are all aware, to a different extent, I suppose. There is something called energy crisis in the world, in Europe. during past year, the wind was not doing what we wanted it to do. Many conventional plants were retired, and all of a sudden there was a shortage of generation. And then people realized, well, something is not going well here. You don't have storage, or at least not sufficient storage. So the issues of should we completely retire conventional plants? Should we build some new ones? I'm not going to go into that. But there is the issue of variability and uncertainty of renewable generation. Now that, coupled with modeling issues related to this generation, which we still didn't develop or understood at the level as we did with synchronous generators. Synchronous generators have been with us for about 150 years. So I don't think that there is any aspect of modeling or operation of synchronous generation or synchronous generators that as a community, we don't understand. Wind and solar generation has not been with us long enough, at least, well, certainly, definitely not 150 years, maybe 20 years or so. We still are, I would say, learning about these technologies, developing models, not necessarily always sharing them freely, because it's still high competitive advantage for manufacturers of these generators to keep things a little bit wrapped, in particular control systems. And control systems are essential for the operation of the system as a whole. Uncertainties related to ICT communications, for example, were always there. There was always some latency, broadband dependence, etc., etc. But now, when we are more and more reliant on communications in all directions, the uncertainty associated with communication systems is also becoming very much important. And from the resilience point of view, uncertainties about the weather forecasts, climate changes, very, very topical thing these days. You know, there's a climate change meeting coming in Glasgow next week, I think, or next month, maybe next week, probably. And the breaking news this morning was that Australia accepted targets to reduce, to go to net zero by 2050. So this is a big change coming from Australia compared to what I have said before. Some people will be there, some people won't be there, but the weather and the climate are becoming a big issue, which is down to earth, to our level or level energy companies or end user customers associated with money. Someone will have to pay for it. And in most cases, however you put it or polish it, we as end-use customers end up paying a portion of it, smaller or larger, in addition to all incentives. If you look, I was just looking at petrol prices in the UK. We had a shortage of petrol a couple of weeks ago because we didn't have drivers to drive trucks. So there was shortage of petrol on pumps. And now petrol is definitely not because of shortage of drivers, about 10% more expensive than it was 2 or 3 weeks ago. So these things are interconnected somehow. Anyway, the other thing that goes with uncertainties is not only uncertainty of models, if you're not familiar with, uncertainties of weather, it's uncertainty of the operating regimes of the system. One is driven by markets. So when the electricity is cheaper in one part, you will tend to import it from that part of the world, providing that there is sufficient capacity. Again, another very, very recent news, this morning actually, again, breaking news, the push to increase capacity of transfer between countries in the European Union to 15%, which is great. It doesn't exist yet. In some cases, even less than 10% exchange between different countries is possible. There was a recent discussion about the situation in Spain, where they have 2 or 3 interconnectors with France, and the exchange is far lower than 10%, which is current requirement, let alone 15%. So to shift power between different countries when electricity is cheaper in one part than the other, or where there is a green or renewable generation in one part, so shift that to the other part of the system, store it there and use it later on, and so on and so on and so on. Now that's one thing. The other thing is variability in wind. So wind blows differently, sun shines differently. If you try to maximize that, assuming that you can exchange the power between different parts of the system, then what you do, then you have a load which you have to follow, or if you control the load will follow generation, but this is still some years away. Now, when you put all this together, then you have to develop, obviously, scheduling of conventional generators. And because this changes on an hourly or even less than hourly basis, your scheduling, your operating patterns would be very different from what we had before. Remember, 20 years ago, what we had? We had a load profile and synchronous generator profile, which followed the load. There were no PVs and wind. So you knew every hour what the load will be. You commit certain amount of generation and you go on. But this PV and wind changing differently on hourly or half an hourly basis. You have constantly moving target. You have constantly change in operating condition. Now, what I tend to say is, in this new environment, we have temporal and spatial variation in renewable generation. And I sometimes get asked, what do you mean, spatial variation in renewable generation? They are not moving. So if you have a wind farm installed in the north side of the country, it's there, it's not going around. It's true. But if you take a system as an example, a system like this, which has different renewable plants at different locations, and because of different profiles, at one point in time, say whatever that is, 6 o'clock, is it 6? I can't see from this angle. Yeah, say at 5 o'clock in the morning, the wind is blowing at these 3 locations, and there are different profiles. 5 hours later, wind stopped there, and it's blowing a different location. And then 5 hours later, again, at different locations. So what do we have? We do not have renewable generation plants as a physical assets, be they wind or solar. We don't have them moving around the system. Who cares about that? What we care is, where is the power injected? And the location of power injection changes. So from that point of view, if you decouple power injection from physical location of the plant, you do have temporal and spatial movement of renewable generation, because injections are coming at different locations. For every new location of power injection, you will have different load flow in the system. So you have completely new situation. And that is changing on hourly or half an hourly basis at the moment. The push is to do it in less than half an hour, but it's going to take a little bit of effort. So challenge there is, how do you model? How do you model uncertainty associated with load, which is also temporal and spatial, cars, electric cars, for example, which not only inject the power from different locations, but they physically move. So you have, I'm not talking about one car wouldn't make a difference. But I'm talking about loads of cars, many cars. So at one point in time, say during the night, they are distributed across the city and they do something. What do they do? If we don't have network observability connected to the previous discussion, we don't know what they do. Do they charge? Do they forget to connect to the network? Or do they sell electricity because they are fully charged? Whatever they do, we are not entirely sure. But what we do know, there are loads of them spread across very wide geographical areas. During the day, they converge, they congregate to a few points with tens, maybe thousands of them at one location. Again, if we don't have observability or a way to extract that observability, we don't know how many are there. Are they selling or buying electricity? Are they charging or discharging? But they are definitely in different locations. So you have physical movement flow, and you have movement of power injection because of renewable generation. There's a lot of uncertainty there. Now, with all this together, storage is another thing. If you have renewables, you need to have storage because you can't use sun during the night unless you store it during the day, in particular in countries like Cyprus. Lovely sunny weather, but the sun, unfortunately, you may say fortunately, but the sun is not shining during the night. So if you want to use a lot of sunshine during the day, you have to store it somewhere. And if you can do that efficiently and in sufficient amounts, you probably would be able most of the time during the year to run on sun only. But that is a challenge of storing that. So with all these uncertainties, thinking about the solving future problems in a deterministic way, as we got used to, and as we, us, professors, academics, teachers, as we taught our students in the past, that is not going to work. We will have to rely more on non-deterministic way of modeling things and analyzing things. And then the third one is controllability. Synchronous generators and devices we had in the network for so many years in the past. We'll learn how to do that. Now we have new type of things, which we are understanding, trying to understand, but the control needs to be faster. Many of these devices are electronic based. They react instantly. So we need to be able to control them faster and probably to control them post-festum, after the disturbance happens. Because having enough money to invest in system design, which will be resilient to all eventualities, this is the time long gone by. Because investment now is mostly done by private shareholders. They want to invest in the system and to get something out of their investment. They want a return. They can't wait 30, 40, 50 years for return. They want return sooner. If they want return on their investment sooner, they probably, I'm not saying they are, but they probably would shy from investing enormous amount of money in the system and waiting for payback 50 years. If they are going to invest less, there will be some risks associated with a system like that. Something may not go exactly as planned. So this control will have to be control that accounts for possibility that something is not going to go well. It has to rely on controlling many more devices. And certainly not large devices only concentrated at a few locations. It would have to go to controlling devices which are more spread around. Now, with that in mind, risk-based control that will not be absolutely perfect, but will guarantee certain level of security, if you like, will have to become more and more accepted. That risk, you may have a risk of 0.00000001%, which is practically no risk. But you may have a risk of 10%. Now the question is, which one are you happy to accept? And as you know, risk is probability of something going wrong and the money and the cost of it. So how much money are you willing to risk or to pay if your risk of something going wrong is low? Or if I want to invest 10 units, I can accept one failure per year. Can I afford that? If I can't afford to have one failure per year, the amount of money I have to invest will go up. So balancing that on risk of something going wrong and cost of that with investment is how the control will have to work. This is not there yet. But if you listen to what people are talking about, both resilience of the system, design of the system, observability of the system, there is no other way. There is no way of designing a system which will be absolutely secure for all possible combinations of power flows due to either market or load or generation variation. So you will have to accept probability of something going wrong. And the question is, what is your, if you like, threshold of pain? How far can you go before saying, look, we have to accept that there will be a problem once in N years, and that will cost us this much. Can we design a system, including controls, that will ensure that? So these are big challenges, and each of them has many sub-problems that people around the world in our and other associated areas are working on. I'll show you some examples now how over last years we try to solve them. And these are the three challenges that we are trying to, are trying and will try to address, which are exactly the same as I specified initially. So there is, one is data, handling the data, the other is the modeling, and the third is control. Now, when you look here, what I specified as potential, I wouldn't say solutions, but the way to address these problems. In all of them, it says new skills of the workforce are required. I'm talking from the practical aspect. I'm not talking about academics. I'm talking how people in real world will run their systems in the future with existing fleet, with existing workforce, people like me and younger, obviously, but not many years younger, who were trained in classical electrical power engineering or communications or mechanical engineering. Will this be a workforce suitable to address practical challenges that the system will be facing over the next 10, 20, 50 years? Probably not, because different structure of the system is coming, different problems are arising. So you will have, we will have, they will have to do something with the workforce, either retrain, reskill, but there is a level up to which you can retrain me. So probably they would need to replace me in a due course with someone who is more skilled in IT or in data analytics, or maybe even in social science, in communications, because that will be the system that these people will be handling over their careers. And then when you look at the areas that are identified, not because I'm inventing something where I'm particularly smart and computer science, it's other people are talking about the same thing as well. I just try to group it in the same kind of clusters. So these are the areas which are not traditional engineering areas, which are proliferating in engineering systems, or rather in a system of systems, which is the thing that we are trying to deal with. And this is the group of people whose work I'm quoting here and discussing in a way. They all worked or are still working with me over last maybe 5, 10 years in trying to address some of these data modeling and control aspects. And you will see how we we handle that. The first thing that I will start with is probabilistic, because this probabilistic and uncertainty thing is a theme which I think goes through all the layers of any system that we discussed before. And it goes into modeling, into control, into data, everywhere. So obviously modeling things using probabilistic distributions, be they normal, beta, gamma, whatever distribution, but not as a crisp number, not as a deterministic number. That's one thing that we started doing many years ago in all studies that group of people who is or worked with me use. We try to model things in a non-deterministic way. And then the thing that we did, one of the things, was risk of small disturbance, instability. So combination of risk studies, stability studies, and sensitivity studies. So sensitivity, which is sensitivity of a single parameter or sensitivity of a group of parameters, including correlation between those uncertainties and sensitivities. So to find out what is the global effect of uncertainties in different parameters to risk of something going wrong. So that led us to study. Example here is about importance of load modeling. But that was what people who did it. This is Dr. Yue Zhu from his research and his PhD thesis. Example is load modeling. The question that I was trying to answer through the work of my collaborators is, do we need to model things accurately or accurate enough model is sufficient? Accurate enough, not from the point of view whether this pointer is modeled precisely in dimensions and in functionality, but accurate enough from the point of view what this pointer is used for. Is it important that the model of wind farm with 50 turbines is absolutely accurate? So when I measure performance in any aspect of performance of the wind farm at the point of connection to the system, and then I measure that they match absolutely perfect. Is that important? I'm not giving you an answer. Or it is important that the model of the wind farm is accurate enough so that the effect of that wind farm on the system is accurate. Assessment of the effect. So if the question is stability study of the system, what I want to find out, sorry, this went the wrong way. What I want to find out is how accurate model of a particular component at a particular location needs to be so that my system level study is accurate. And this is example of load models. So how important is to model accurately particular load at a particular location so that I am 99% confident that my stability assessment is within 1% accurate. I can obviously adjust the level of confidence and the accuracy required. So when you look at this, so we have required accuracy, which varies for different type of stability studies. So we did small disturbance, large disturbance, voltage and frequency stability. So how accurate load models need to be at different locations so that our stability studies, that we are happy with the accuracy of stability studies, because this is ultimately what we want. If I can identify which loads in the system need to be accurate, and which loads can be modeled with generic models, then I, as a system operator, can dispatch workforce at those locations and develop accurate models for the locations where it is met. But not for every other location, because that will not affect my system behavior. As I said, this is an example in load models, but it can be done for any other, for generator, for anything else. The other thing which we are doing currently is how quickly and how confident we can assess what's going on in the system and deploy corrective measures. System with renewable generation, different levels of this renewable generation. So what we want to do, we want to assess from the moment of the fault, as soon as possible, which generators are going to become unstable first and to control them. If we control them, the whole system will be stabilized. Now, this is talking about corrective control, not talking about load shedding. So this is talking about corrective risk-based control. When you put all uncertainties in, how quickly can you do that? How quickly can you tell after the stability, right, we have a problem with these 5 generators, do something with them. So we get something like that. Now, what is this? What is this peak there in this deep drop? So this is connection between a threshold of generator angle when you can confidently say that something is going wrong. And this is, and this is the point when you make decision about the grouping. Now, to simplify this, people who do who deal in function stability, you know that there is theory says the system becomes unstable either when individual generator rotors are 360 degrees apart, or if the rotor of any generator is 180 degrees apart from the center of inertia. What we've proven here, it doesn't need to be like that. So once your angle is 130 degrees from the center of inertia, there is 99.9% that the system is becoming unstable. So you don't have to wait any longer. So the whole point is we can make decisions faster and deploy corrective measures faster than waiting unnecessary long time. Now, when you think about what is this unnecessary, we are talking here almost about half a second faster. So making decision, confident what to do half a second faster is a big thing in a power system where you want to act after disturbance and not in investing in a system prior to that. And this obviously takes into account all the uncertainties of renewable generation, variation, connection, disconnection generators, and so on and so forth. The other, this is a part of a bigger problem that we're trying to address, is global system flexibility. So if this is existing system operating point that goes obviously around, we are not sure how it goes, where it goes, but assume that we know this line. And assume that we know where the boundary is, which we don't. So this is something that we still cannot define, but let's assume that we can. We have some idea what this might be. But we may have an idea what this might be with respect to one system attribute, say voltage stability or small disturbance. But do we know as a global stability? We don't, but let's forget about it. So assuming that we know that, with the new system, the operating points will change. Will change because of the uncertainties and variabilities. And then with this new operating point, there might be situations where we are further away and situations where we are closer to the stability boundary. So depending on the level of penetration and location of renewables and load behavior and system operating point, with renewable generation, which is variable, we may have moments when we are better off and moments when we are worse off than in conventional systems. Now, we talked about uncertainty clearly. So this is all uncertain. So we can't be absolutely confident that we know what we are talking about if we don't take uncertainties into account. Now, if you take them into account, so how can we then assess what is the remaining flexibility at the particular operating point? And can we help it somehow? Can we deploy something to solve the problem? If we moved closer to stability boundary, can we apply something to move system away? And vice versa. So we tried to look at it from the obviously multidimensional point of view. So if you have more than one property, this is a combination of small and large disturbance stability. So you have three surfaces here. One is system without renewables, then system with renewables, and then system with applying demand side management to see whether demand side management in the system with renewables will change things. What you can see in this part here, in particular, is that once you apply DSM, the surface, the operating point changes. To what extent it changes? Well, that depends from one system to the other. Now, this is going back. This is complicated. This is just two aspects. It is two types of stability. And system, as such, talking about stability only, we have small, large disturbance, angular stability, frequency stability, voltage stability. Not mentioning other aspects of system performance, losses, reliability, and then resilience as a overarching thing there. So how do you represent all that in a 3D diagram? No way. So what we were searching for a coefficient, composite index, which can account for more than one aspect in one index. And this is example where we came up with an index which demonstrates, which compresses three aspects into a single index. And you can see how this is the blue line is system without RES, without renewable generation. Dashed red line is system with 30% RES penetration, and then dashed black line is system with 60% of RES penetration. So you can see how system is moving with respect to stability where it was without RES. And the composite index, the smaller it is, the worse off we are. The value 1 is good, the value 0 is bad. So we can trace that in the multi-dimensional space with a single index. So this is another effort of the work that we are trying to do. Now, risk, coming back to risk. This is adopted, the idea here is from compatibility work, power quality and system compatibility. But that doesn't really matter. In any system, we have disturbances which are uncertain, and we have immunity, what system can withstand. What the problem is this area here. This is the risk of interference. If there is interference, there is a potential of something going wrong. With different operating conditions, with, for example, more and more uncertain generation, the system, the immunity probably will stay the same. If it's simple, don't put the immunity moment. But the level of disturbance may change. So the risk obviously changes. Or the effect can go other way around. So again, there is the area where these two systems, where the two problems are interacting with each other changes. So what we actually are trying to do is find the risk. Find the risk when something can go wrong. And with it, we looked at it from the point of view of, again, it happened to be load modeling, defining a risk function to assess risk of something going wrong, depending on size, location, and model of the load, and operating condition of the system, obviously. So there is a risk function here better not touch anything. So you can see that the dot curve shows that the risk function is defined depending on the parameters of that curve. You can assess the risk differently, and this is what you get. So the red color indicates high risk, the yellow indicates low risk. So we can identify, for example, the dependence of the time constant. So the third plot on the right is time constant horizontally, and vertically is system loading. So if the time constant of dynamic load is lower and system loading is higher, the risk of something going on in the system increases for a particular location in the system. You can devise these profiles, risk profiles for any parameter in the system, and then what you end up with is something like this. So this is the risk of system becoming unstable. So what do you want? You want this red area to be non-existent. And what we are trying to do is to assess how large that area is. We've done this. This is an illustrative example for load modeling, but we have it for renewable generation, wind, etc. So it can be done for any parameter of the system. And finally, something that, as I mentioned at the beginning, Elias was among the other things known for, is talking about interconnected systems, and he wrote a very good book with photos from here some years ago, which I read with a great interest. And among the other things, that inspired me to do some work with some of my people on modeling, on modeling of uncertainties again in interconnected power and communication systems. So what we did, we used a very simple network, and then we used complex network theory or graph theory to assess which buses in the system, be they power or communication buses, are more important than the other. So either unidirectional or bidirectional graphs can be used. This is from mathematics, obviously. Now you can represent that in a 3D, which we wanted to do, so it gives you more clear vision of what you're doing. So one level is power system, the other level is communications, and then connections between them. The connections between the two systems, obviously. Communication systems is monitoring, so receiving information about the monitoring and sending control signals. And if any of these links is broken, the overall reliability of the system reduces. Now, we defined a new index, which considers weighting of these communication links and power links, weighting dependent on physical properties of communication and power network. Doesn't matter what they are. You can read about that in the attached documents later. But based on that weighted index, you can assess which node in that interconnected system is the critical. Which one should be, let's call it, protected. Now, there are two ways of looking at this. One is the one that we are looking at. Which node should be protected? So if something happens, that we don't have catastrophe. The opposite way of looking at the problem is which node will cause the most damage. We're going to elaborate on that further. So this analysis of vulnerability of interconnected systems is the solution to that we have is far away from the solution. These are only attempts to see how we can look into that. And then we moved on to applications in realistic network. This is a real network of a real power system and real communication system in one of the European countries, including uncertainties that exist with communication system and power systems. And we try to identify these nodes. So which buses in the network are the critical ones? The larger the red circle is, the more critical bus is. And you have IPS or ICT. So you can see which buses in that interconnected large network are the ones which can cause problems, including associated uncertainties. So it, as I said, because we know the system, these buses happen to coincide, maybe accidentally, maybe not, with the real buses that system operators knew are critical. But this is one way of looking the reliability or vulnerability of interconnected systems. Again, this is only two networks, ICT and power. Imagine how much more complex this would become if you start adding other layers. So in summary, the things are not getting simpler. They're not. Probably we have to come up with solutions which are not omnipotent. There is probably not a single solution that can solve all the problems or single control approach. So there might be different things that could help. So one way of looking at the problem is considering the airplane. Obviously, I landed last night with 1 hour and a half delay because something went wrong. And instead of landing in Paphos, the plane turned above the Paphos and then back to Antalya. And that's why. Anyway, so plane, take out the plane. So at the moment, this is our power system. And in that power system, we have a control center or cockpit where the pilot and co-pilots are. So the system, plane, is run from there. The plane is powered by central generation, which are the engines. Now, you all know when you're on the plane that there are these little things. When the plane is going up or down, the wings start to fall apart. When I was young, first time on the plane, looked through the window and I saw the wings are spreading. And I started to worry, what's going on? The thing is falling apart. Well, these little things, they don't fly the plane, but they help with taking off, landing, turning, changing altitude. These are our ancillary services. I suppose that many of you have been to the United Kingdom, and if you haven't, you have heard about Tesco. Is a department store. I think that there might be even Tesco stores in Cyprus. I'm not sure about it. I think they are, but maybe I got it wrong. So the Tesco's motto is "Every little helps." So every little helps is something that we'll have to start considering for solving some of these problems of the system in the future. And that every little, in addition to what we already have, standard control of standard devices. So new things, we probably need to look more closely in how can better control of new sources help. How can energy storage help? And how can manipulation of demand? Demand-side management is something, as you know, which was used for economics pretty much, not from the point of control. But what I'm talking about here, how can we help control a future uncertain system by varying demand, by controlling demand so that we have always such balance between demand and generation that is guaranteeing system performance in all aspects necessary, not in terms of only of energy and economics, in terms of stability, dynamic performance, etc. I am people who know me or read what I wrote. I never ever worked in markets. I don't know anything about markets. I don't deal in economics. I'm trying to solve technical problems only. So what can we do with demand to ensure appropriate technical performance of the system in all aspects of technical performance, irrespectively whether these changes are coming from the market forces or forces of coming above. So, future, those of you who are still interested in doing some technical work, I believe these are the three areas that are already popular and whose popularity will not diminish over coming years. This is all the following two slides. I'm not going to show them. They will be made available to you. So all that I was talking about, and that I probably went a bit faster through some aspects of it, that's all described in this in the selection of papers listed here by the people whose work I use to illustrate the solutions or problems that we were working on. Thank you very much. I lost track for an hour. If you have any questions, I'll ask Christos to answer. Or Mateos over there, so he knows most of the stuff that I was talking about. Yeah.
Professor, I was a little bit surprised when I heard about the percentage of power interconnection between the interconnected grids.
Yes.
And because we are trying to do it nowadays with Eurasia and Eurafrica, energy is very
yeah.
I'm wondering, this is the performance of this interconnection between the various countries.
Yes, it is surprising how low it is. And this morning, I don't watch news normally, except that I'm traveling, and this is an opportunity when I travel. So I woke up in the morning and switched on news, and there are two breaking news. One was about increasing interconnections between countries in Europe, increasing it to 15%, realizing that 10% of this current target is still not achieved. The other day, there was discussion, as I mentioned, between Spain and France, where interconnection is very, very low, far below 10%. And the one issue, important issue, is physical ability to transfer power between different countries. So even, for example, you and I want to exchange power between our two countries. If there is no physical infrastructure to do so, we can't. So we need to have infrastructure first. But the other problem is, even in the countries where there is infrastructure, for example, between Spain and France, there is infrastructure to exchange more power than they are doing at the moment. And that's, I just use that because it was the latest news, but that applies to any other country in Europe. So even when there is physical infrastructure to exchange power, people from different TSOs are not doing it, because in many cases, in particular for some of the services discussed here, there is no regulatory framework how to do it. They know, I mean, I can send power to him, he can send back to me, but there's a money involved in that. So how do you officiate transactions in terms of money? That's what people are working. There's a lot of work going on now on regulatory aspects for ancillary services, for demand participation, for renewable participation. How do you compensate market participants for providing certain services? There are a lot of people working on that without considering physical requirements for that market to be inactive. And someone obviously came to the conclusion that, why, right, it's good that half of you are working on market, but the other half should actually work on, if you develop a market and regulatory framework, can we actually do it? And then they came up to realization that if there is no 15% interconnection, many of these things will not work. And they started talking about that now. It's essential for all of these discussions that I was talking about. It is essential to be able to shift power from one part of the system to the other. If there is no infrastructure for that, you can't do that. If there is infrastructure for that, you will do it only if you are financially compensated for that. So these are things, it depends what's first, chicken or egg, but these are inseparable things. It's a different probably answer to the question you asked, but I was trying to round it up somehow.
Professor, for the interesting presentation. I would like just your opinion as to Cyprus by the power system of Cyprus by its nature is an island power system, so we don't have any interconnection. So due to several geopolitical reasons, we may not have. Future, we don't know. We will see about that. In addition, the national plan we envision to increase the penetration of renewables by 4 or 5 times within the next decade. So this will lead to a very low inertial system. So in this case, what do you think? What's your opinion about it? What should be the most important aspect that we consider in order to ensure the stability in such low inertia power system?
I obviously couldn't talk about everything in this lecture, but another group of people working with me is looking at the issues of low inertial systems. We don't look in 100% renewable system with zero inertia, because we're looking at which is possible in Cyprus as not being interconnected. We're looking in increasing level of renewables. Now, if the system is totally without inertia, then the issue of frequency comes up. Do we need to operate at 50 hertz? Does that system need to have a frequency as unifying quantity? Right, we have loads which operate at 50 hertz. But we have converters as well. So if I put a converter in front of the house, it can convert whatever frequency is coming to it, and then the loads will work normally. Now, if that happens, then all the issues of angular stability that we are talking about today disappear. What is angular stability if there are no rotor angles? So we are talking about converters. Now, stability still exists. We have a recent task force on definitions of stability, was published a year ago. Introduced this resonance stability as a new aspect of stability to address the issue of systems with low inertia and systems without inertia. So resonance between different converters, and transmission lines, these are the things that do not involve inertia, that do not involve any rotation of masses. These are purely electrical phenomena. So the issues like that will appear. Now, coming back to practicality of, say, islanded system operating completely without inertia, that is possible. If you have wind, converter connected, if you have solar, fine, and loads of storage. So you won't have a need to have any other generation. But thinking about it, the installed capacity of wind and storage will probably have to be multiple times higher than your maximum load, because you have to ensure that whatever happens with renewable generation, you have enough energy to supply the load. You may have a system points in time where you supply the load from renewable generation and storage. It may be when you are supplying generation a load only from storage, but you don't know when that is going to happen. So reliance on high installed capacity of renewable generation and high storage is necessary. Technical aspects of running a system like that is a different thing, but it would be related to stability of control loops of controllers, interaction between different controllers. Probably keeping some conventional generation in some corner of the country quietly running would not harm. That's maybe pessimistic, maybe not optimistic enough. It is possible to do it without conventional generation. I honestly think, maybe I'm wrong, I honestly think we are not yet at the level of sufficient understanding from the theoretical and practical application aspects point of view, how we will run 100% no inertia or zero inertia systems. Because protection will be affected, a lot of things will be affected. So we'll need faster protection, so we'll have to refit the system. So there are a lot of issues, apparently tiny or appearing tiny issues, which we are not, I don't think we are mastering yet well enough to be able to say, okay, from tomorrow, no conventional plants, no rotors, just go with wind, solar, and storage. So that's why I'm cautious in saying this, some hidden corner with a conventional synchronous generator.
President, thank you very much for the inspiring, let's say, talk. You talk a bit about uncertainty. And,
yes.
Where were you?
So
No, I saw him sleeping. So.
Yeah, sorry.
I'm joking now, you know.
So yeah, my opinion, uncertainty of the power uncertainty of renewable energy sources is a factor that limits, let's say, the penetration of renewable sources. Do you think that storage will be a dominant factor in the next year in our systems, or relative utilities should also consider some non-wiring solution, the provision of flexibility services like flexible resources in liquid systems?
There is a lot of potential at distribution network level to help to a different extent with different aspects of operation of transmission network. Now, when you're listening to me, you say, what is this person talking about? No quantifiers, different extent, different aspects, and so on. Why I'm saying that? I'm saying that because I don't believe that anyone actually knows what is the real extent of what can be done with whatever is available distribution network, and to what extent that can contribute to the transmission network. This is what we are trying to do. We are trying to address exactly that problem. What is real potential? There is a potential. We can control demand at distribution level. There are pilots in the UK which demonstrated we can control the voltage at transmission level, we can control the frequency to an extent. So we can control demand. We have PVs and wind connected distribution level, and we will have storage. In some countries, in Germany, for example, they have a lot of batteries in Bavaria associated with PV. So there is that bit there. What we need to have now is a control of thousands of small devices that will provide support at a high level. Now, many pilots that I'm aware of, certainly there are some others I'm not, are talking about how are we going to control, let's say, 500 loads or storage devices to control the voltage at such and such bus, where the transmission network is connected to distribution network or distribution network. As you know, many distribution networks are not connected to a single point transmission network, but to many points. So if I'm playing with the loads in one part of distribution network, I will change load flows and maybe other aspects of that distribution network, and I will affect other buses in transmission network. To what extent? I don't know. We don't have demonstrations about that. So there is a potential, and that's why I said every little helps. This is something that we have to study, but we have to study it with realistic assumptions. We can't go for a solution which relies on demand side management, for example, which I particularly like, without knowing what's the actual potential. There is a project that Matthäus and I were working together before he moved back to Cyprus, which involves 8 TSOs in Europe, where one aspect is coordinated use of storage and the other is demand across border to control transmission, transfer of power across different systems. So we did survey in 8 interconnected transmission networks in Europe. And we found out that currently from the storage, there are two hydro plants, nothing else, no batteries, 2 hydro plants as a storage. Demand, about 12% of demand, total demand is controlled. Now, what can you do with 2 hydro plants, which are where they are, they're not distributed? And what can you do with 10% of controllable demand? We did studies, not much. Whether you connect or disconnect all of the demand at the same time, at whatever time you want, the effect on interconnected system is minuscule. And what is that demand at the moment? I'm talking about reality, Europe. No case studies which are invented. It's reality. These demands are very large industrial plants and these 2 pumping stations. So 300 megawatts power plant becomes demand when it pumps. When it generates, it's a generator. Now that's not really demand, because if I need to reduce something during the day, I can't connect or disconnect hydropower plant, which is doing whatever it's doing. The other things are cement factories, metal, aluminum or steel smelters, and things like that. There is no reliance at all on distribution network load. And as you know, cities, big cities, that are huge load. But manipulating a city as a load requires very good coordination of various things, definitely uncertainties, because we don't know what we have, and we don't know who will participate in it. There might be people say, look, one selling point is, okay, if you let me manipulate your devices, you will save 50 euros per year. But these are the figures which we're talking about, actually. It's not 500, it's that kind of money. Some people will say, oh, 50 pounds per year, or 5 euros per month. That's good, let's go for it. Some people will look and say, can't be bothered. Some people will do that because they believe that participating will make world better, which is all positive. But we don't know. We actually don't know how many people and where would agree to participate in that. And you can't, because of obviously human rights and other all worthy reasons, you can't connect or disconnect people at will. You have to have their agreement. So imagine if you are a distribution network and 2 of us are connecting points. And there is a system behind us. And the system realized that at a particular point in time, his load is one connected point and the other. He has to go 10% down and I have to go 20% down. All the requirements of the transmission network. But then you may be radio towards the end, but the top is already meshed. So if I start manipulating loads in that corner, that will affect both him and me. Maybe we will not go 10%. Even if I do whatever I want with these guys there, with these loads there, maybe that's not enough. And I don't know whether it's enough or not. But the other thing, I may find out that I need to manipulate that particular corner. And when I go there and ask, okay, guys, can we do it? Say, nah, not interested. So this is what I'm talking about. We actually don't know. Nominally, these loads are large. Technically, we can connect and disconnect them, and they could help. But we actually don't know what that help will be in real systems, because we haven't tried that. And the problem technically is very complex. And I haven't seen studies yet which do that from the realistic perspective, controlling many things at distribution level and affecting simultaneously many buses at transmission network level. We are working on it. But, in a year or so time, I'll come again and I'll tell you how we did it.
You had a last question.
I had a question, yes.
Give you the floor.
So I had a question about the risk and the relationship of risk with the data and the probability distributions from which you find out the risk. So when you talk about figures like 1%, 0.1%, it's okay, find the risk. But let's say if you are interested in risks like 10 to the minus 6, 10 to the minus 9, how can you find the data to, let's say, create distributions about your uncertainty in order to evaluate the system with that kind of risk?
These are risk levels that people dealing with some other systems are probably accustomed to, dealing with nuclear systems, dealing with space systems, dealing with communication systems. But these are not people working in power.
But even in communication, they don't know what the time.
No, they know what.
Yeah, well, but then how do you measure? It's not something that it's what the before. Something happened now. You say one event happens every 100 years. Happen now and happen in a year. Does the probability change or I don't know? Don't have enough data.
Yeah.
So basically, what they're pushing now forward in national grid, or in data infrastructure in general, including national grid, to apply the stress test of the infrastructure against the set of scenarios, 1,000 scenarios, they identify, let's say, the breaking point for which you try to put a value of risk or value of experience, then that drives everything else. And drive your investments, it's not the breaking point, drives what Marcos asked about that are needed, so that to stay below that threshold. So basically, because of the lack of data, they are forward this stress test, which should be overseen, of course, by the
I see you.
I just wanted to ask a related question. You identify the risk. You take any actions to mitigate the risk, to balance it out by changing the topology? Or
That's what we are. This is one of the research areas that my team is working on, is risk-based control. So design a control solution that will reduce the risk. But in order to do that, you have to find out what the risk is. And then with the controller in place, properly, you tune the controller so that over thousands of scenarios, the risk, that area which I showed in one of the slides, is reduced. So that doesn't mean that your control will work always, but when you take it from the all possible scenarios with the controller in place, probability of something going wrong and hence consequences of that will be reduced. So that's why I was talking a risk-based control.
There's
two ways to do that. One way is to design a controller which is covered over, which may be more conservative, or another approach is more adaptive, where you may, because you mentioned real time, so you try to measure at what state the system is, so that you make adjustments to the controller as it gets worse.
We are working with the other one. So trying to rely, the second one, trying to adjust the control based on what's going on in the system. But that is again requiring good observability of the system.
The real-time risk assessment.
Yes, there are. We don't have a issue with problems. We have an issue with solution.
Let's thank our. I know it's great to have a teacher teaching us. After we will go, I think we have a few more minutes if someone wants to discuss something that excellent. Well, thank you so much.
So, do you want to email this to you? Leave it here.